This is gonna be a nice one. So it's called primal-dual method for approximation algorithms. So from the previous class, you have seen two ways to come up with or to design an approximation algorithm. One is kind of ad hoc, like be greedy or do something else. And then there is another more principal one, which is to do LP routing. Right? You start with integer program, relax it to LP, solve that, and route it. So for that, you need to call an LP solver, but the development is kind of, you need LP. For this today, I'm gonna talk about a new one. It's called primal-dual. So the design is still centered around LP, but for this one, we just use LP as a guide for designing algorithm, and we don't even call LP solver. So it's going to be fast, and it's going to be less black box. We don't just solve LP in the black box way. We really get some algorithm that in every step we understand it. Okay? And it's going to be quite robust in the sense that because we understand everything about it, you can make it work in the online setting or dynamic setting, which for the online thing, I will talk about it next week. But the key message that I want you to get from this class is that not just like last time where LP is some powerful black box, LP can be a tool for thinking, for designing algorithm. Okay. So let's start with the first example, which is set cover. You have seen this problem several times now, but let me just recall again. So it's a problem where you have a universe E, right? You have a bunch of sets. So you think of elements in the universe as vertices on the left. Every set are vertices on the right. And then each set have some weight on it. And what happened? And what we want is a set cover. That is, we want to choose a collection of sets such that it covers every element. Right? We have seen this before, but for today, we will have more constraint on the instance. That is, I promise you that we have F-bounded frequency, which means that every element is contained in at most F sets. So the degree of every guy here is at most F. Okay. Do you mind if I close the door? It's kind of okay, good. So for vertex cover, right? Can anyone tell me how does vertex cover is a special case of this problem? So F is what in this?
2.
2, yeah. So F is just 2. So for vertex cover, every guy here corresponds to an edge. And so it has degree 2. Okay. If an edge is an edge UV, then it's contained in U and V, something like that. So this is just a more general problem than vertex cover. And for vertex cover, when F is 2, you saw 2 approximation algorithms based on LP routing. And for set cover, you have seen log n approximation based on both LP routing and greedy. So today we're gonna see F approximation for F. So this is better than log n when F is small. Yeah. Okay. And so the starting point of how to design the starting point of primal-dual method is this. You just always start with writing IP and write its LP relaxation and its dual. Okay. So we have seen this IP, the IP formulation of this problem already. So I will just not repeat. I will just read through it. That is, we just say that every set S, you kind of have this thing which say that this is 0 or 1, right? You indicate whether you choose a set S or not. And for every element, you need to cover it once, and you want to minimize the total weight of the sets of all the sets that you choose. So you have seen this IP formulation of set cover, and then we just relax it. Once you relax it, you just throw away the integrality constraint. Yeah. And I also claim that you can just throw away the inequality XS at most 1 as well. And this is just because if you know that the optimal solution will not set any set to have value more than 1. Okay? Because if the set S have value more than 1, even if you reduce it to be 1, you get better objective, but the constraints are still satisfied. So you don't need to, you can just throw this thing away. It's redundant. Okay. So this is the LP relaxation of the problem. Okay. You just have that the sum of every set containing an element is at least 1, and minimize the total cost. And once you have the primal LP, next you derive the dual. And I will not go through now how to derive dual. You can see and verify that it is the case, but let me just read through it, try to interpret it. Okay, when the dual looks like this, you introduce a variable ye, right, for each of the constraints. So you have ye, and what you want to do is to maximize the sum of ye, such that for every set, the sum of value of all elements in the set, sum of ye for all elements in the set, this thing is at most ws. Okay, and ye need to be non-negative. And okay, once you dualize this LP to get dual, maybe the first thing you should try to get is intuition. What does it do? Okay, and the interpretation of this is not complicated. You think of it as you try to pack element. It's an element packing problem in the following sense. So first of all, you want to put large value to y to add to each element as much as possible, right? So you try to pack this value into elements, but you have a constraint. That is, you cannot pack too much. For every set, the sum of the value of the element in the set need to be at most ws, right? So now you think each set is like a packing constraint. It's a constraint that you cannot pack too much. Say that you cannot pack too much. If you have a set S here, and this guy, and this is ws is I don't know, something, 10. Then any elements here, the total value of the elements that is contained in S cannot be more than 10. And each of the set gives you this kind of constraint. So that's how you interpret this dual problem. Okay. So that's the starting point. But question about how does this say intuitively? It's like a packing element, right? Okay. So that's the starting point. You start with write LP and its dual. And now, once you have the dual, let me just tell you the algorithm. So I will just give you the example of this algorithm first, and at the end of the class, we will try to abstract out what is the template, how to design primal-dual. Okay. The algorithm is like this. So what you do is that you have this dual variable. This is going to be fractional dual variable, and you have a primal integer solution. Okay. So that's the first step. Just start with initialize everything to be 0. Okay. And now, what we do is this. Just say that, okay, look whether there is any element that is not covered yet. That is not covered by T, by your solution T. T is your solution. If there is something that is not covered yet, just look at that element, E, and then you increase YE, the dual variable for element E. So increase this value YE until some dual constraint is tight. Right? Because think of dual packing problem, if you keep increasing the value of some element E, you cannot increase it indefinitely. Right? At some point, it's going to be tied by some constraint here. So let's say that it's tied by the constraint associated with a set S. Then it just means that when you sum over all for this thing will be tight. That is, summing over all elements inside S, summing over all E prime inside S, Y of E prime. This is now tight. Okay. So when that happens, when you keep increasing YE until things are tight, then you stop. And if it's tight because of a set S, then what I do, I will just add a set S into my primal solution, T. Okay. And then repeat. Okay, so let's see some illustration, right? So suppose that this is your current, you run this algorithm. This is your current set T. It covers a bunch of elements. You look at some element that is not covered yet, increase YE until some of this red guy is tight. Right? You keep increasing YE, some of this red guy, the set that contains it must be tight at some point. If one guy is tight, then just add the tight guy, the tight set into your solution T. Okay. And if you keep doing this, then it is clear that at the end everything is covered. Right? Like you just stop when everything is covered, And the algorithm run in polynomial time, and you really understand every step here. It's really, nothing is black box. Okay. So now the question is how to bound the approximation ratio. Question about the algorithm description. Okay. So you see, like, at the note that at the end you want t, but the algorithm here we maintain y. Y is like something that you use just to help you construct the final solution. Y is a dual variable. You maintain y, but at the end you just want t. But y plays a crucial role in your algorithm. So like you use dual information to help you, although you don't need it at the end. So let's see how to bound the approximation ratio. Okay. So my claim is this. My claim is that the total weight of your set that you return is going to be at most f times optimal value of the dual problem. Okay, I will prove this later, but if this is true, let's see why we are done, right? I claim that if this is true, then T must be F approximate solution. And the reason is this. You know that the weight of T, which is the integer solution, is at least optimal value of the integer program. That's always true. And opt of P in the integer program is at least of the LP, which is the same as of dual by LP duality, right? Dual and primal LP have the same value. But now, this guy is at most F times of P. So which means that these two numbers are sandwiched by these two numbers that are just F factor away. Right? So it just means that these two guys must be within F factor within each other. So you just need to bound that this is within F factor, but you bound something stronger. So now, so with this claim, you see, right, now we get F approximation. So let's now prove the claim, the key lemma. So let's prove it. So how to prove this, right? So this is an important step in the analysis. Okay. So the first thing to note is that for any set S in your solution T, we have what? We have a tight constraint, dual constraint. That is, WS is just exactly the same as YE. YE is in S. So this is what we know on how we construct this. The only information we know about how to, like, about every set in our solution is tight. Okay. So let's exploit this fact. Okay. So the weight of T is just everything in T, this weight. Which is what? Which is just this thing. WS is tight, so you get this. Okay. And let me just try to swap the order of the sum. Then what you get instead is the sum over all elements, right? And then this is T, S in T, and E in S. Okay. But this is the same, like, you know that this is just summing over all YE for the same, like summing over YE, the same YE for many times. Right? So just write it like this. This is just YE. And the number of times that it's just you count the number of sets such that E is inside S. Okay. Make sense? And this is just at most F, right? Like even if I don't count, even if I don't have this constraint that S need to be from T, the number of set that contains E is at most F anyway. So this is F times sum YE. Okay, now I claim that this is at most op of D. Why is that? Why is it the case that sum of YE is at most op of D?
The sum of YE is just the objective of the dual?
Yeah. The first thing to know is that sum of YE is just the objective of the dual. Why can it be more than optimal value of this dual? Like this is just YE that we construct. Why is it at most op of D?
Because like the theoretical optimal is the optimal, so like if it was bigger than the optimal, then like you would have a contradiction.
Yeah. So yeah. The point why you can say that our YE that we construct is at most op of D is because our Y is feasible dual solution. That's why you get this thing, right? So and this is the case that so when you increase Y, right? We stop at the moment that sum of the constraint is tight. We never violate any constraint in the dual problem. So Y is indeed a feasible solution. It respects all the dual constraint. It means that this is a valid solution to this dual problem. So so the value must be at most the maximum value because it's a valid solution. So that's important, like, because we always make it feasible. Okay. Yeah. And so this is one important thing where you make sure that your Y, this is the first important thing, Y is feasible. That's why you can relate the cos here with the dual, with the op of dual. And another important thing is the tightness. Why? Because if you don't have tightness, what you get is this equality, which looks like what? Which looks like this thing. And it would look like this here. Without tightness, you just get this inequality in the wrong direction. You cannot bound anything here by this part. Right? So you see, it's important that we use tightness, so that we get equality instead of the wrong direction inequality. Okay. And with this analysis, then we are done. Right? We get approximate algorithm. Okay. So question about this. And yeah, so you see that nothing, like everything is not black box. We just kind of, what we do is we derive dual LP just to help us design an algorithm. And every step is very easy to interpret. And I want to encourage you to try to see what happens when you just interpret this algorithm for vertex cover. What happens when f is 2? Okay. It's going to be clear what's going on. So try to run this algorithm when f is 2 and describe it when in the graph language. Okay. And it will give you two approximate algorithm, which is like a simple one, instead of using LP solver. Okay. Now, let's see more advanced, like just another example before we abstract the philosophy of this. The next problem is called feedback vertex set. So this problem is as follows. You have a graph, and let's say you have weight on each node. And what I want to do is I want to return something called feedback vertex set with smallest weight. So what is feedback vertex set? It's just a set such that once you delete it, there's no cycle in the graph. So once you delete this set, then the remaining graph become a forest. It has no cycle. So for example, this is in this picture, if you delete these two nodes, right, then the graph becomes just a path like this, and it has no cycle. And the best feedback vertex set in this graph is just these two nodes, as smallest weight. And yeah, for like applications, like this problem have something to do with something in OS. The intuition is that the cycle usually correspond to deadlocks. And what we want to do is to make sure that there is no deadlock. I don't know much about this, but yeah, can look it up if you're interested. Okay, but what I will show you is that I will show you log-n approximate algorithm in polynomial time. By the way, the state of the art is better. It's two approximate. It's two approximation and it's fast. It's near linear time. And it's actually use primal-dual as well. But today I want to illustrate the idea in a simple way. So I show you log-n one. So before we start with writing down primal and dual LP, I need one step, which is needed in the algorithm. That is to simplify graphs. So just think about this. Like when you try to delete cycle, then you can simplify the graph like this. That is, suppose that there is some node with degree 1 in the graph. Right? I claim that I can just remove it from the graph. It doesn't matter. Because no cycle will contain a degree 1 node anyway. That is, if I after I delete this degree 1 guy, and let's say I have some solution that, okay, I delete this guy and the graph become a forest. This same solution would work in original graph as well. So you can just keep deleting degree 1 nodes. And the next thing is that, suppose now that I have a long path like this. What I can do is I just can contract this whole path into a single vertex with minimum weight. So I have this long path. Everyone here has degree 2. I can just contract everything to this guy with minimum weight. So I get just this. And the reason is here. You know that no matter what, the node that have higher weight will not be in your solution anyway. There's no reason to pick any guy with higher weight than the minimum guy. Right? If you want to delete this guy, to remove this cycle, you can just instead choose 3 instead. Okay. So you with me? Like any guy that has non-minimum weight cannot be in the solution. Question about this?
Why isn't 1 included in the, like, why wouldn't it have 1?
Oh, I mean, because I just contract this path, right?
So how do you determine which part to contract?
Oh, I only look at induced path, which means that every node here have degree 2. Yeah. All right. Okay. So now let's see, why do we want to do this at all? I claim that once you simplify the graph is quite nice. So in what sense? So suppose that I said that the graph is simplified. Once you keep prune and contract until you cannot do. Okay. Then I claim that if the graph is non-empty, after you simplify it, then it must have short cycle. Cycle is short. So first of all, if it's not empty, it must have a cycle. Because every node have degree at least 2. Right? If you don't have cycle, then you are forest, and forest must have a leaf. But now mean degree is 2, so you must have cycle. But I claim that the cycle must be short too. Okay. So let's try to prove this. And the proof, let's for a moment, instead of say, so you know that the mean degree of this guy is 2. But let's for a moment assume that the mean degree of graph is 3. Okay. And let's prove that there must be a short cycle. So if the mean degree is 3, And suppose that you just start BFS from any node. What you get is that, okay, first level you have 3 nodes. But in the next level, every node here must have at least 2 children. So as long as if you go on the level and you don't find cycle yet, the number of nodes must double at every level. Right? At every level, the number of vertices must double if there is no cycle found between the branch. So, and without finding any cycle, you can go on like this only for log n times. Because you cannot double the number of nodes by more than log n. So this is at most log n. But let's say that once you find a cycle between branch, let's say like this, then this will give you a cycle. If there is an edge connecting between branch, then you get a cycle, and this cycle is short, right? Because this is log n, this is log n, this is 1, so something like 2 log n. So you see, if the graph has mean degree 3, there must exist short cycle. So, but our graph might not have mean degree 3. It can have some node with degree 2. But I claim that it's essentially like degree 3, mean degree. Like the graph essentially have mean degree 3. Why is that? In our case, when the graph is simplified, okay, mean degree is 2, can be 2, but you know that any degree 2 vertices cannot be adjacent with each other. If there are some nodes with degree 2 that are adjacent, like A and B here, you would have contract them. Okay. So now it means what? If you just do the same thing, start BFS, okay, some node might have degree 2, so it can have just 1 child. But now the next step, it must have degree 3. So for every node, its grandchildren must be at least 2. You might have this, and then this. But no matter what, the number of grandchildren is at least 2. Which means that for every 2 levels, the number of nodes must double. Right? And now you can do the same analysis. That is, okay, you just keep going on for maybe 2 log n levels now. And you must find it must, like, at some point, after 2 log n level, there must be some edge that go between branch, and that will give you a short cycle. So you get the cycle of length 4 log n. So, okay, what we get is that any non-empty graph, which is simplified, will have short cycle. Okay, now we are ready to get like to do our template. So we just start with LP relaxation. How to start with that? Let's try to do it together. We need to start with IP first, right? So suppose that I define define this set C to be a set of all cycle. Then what I can do is maybe I can just create a variables, right, for every node. Because our solution is like a subset of nodes. So we again create an indicator whether we choose this node V or not. And we want to minimize the total cost, the total weight of the set that we choose. Can someone tell me the constraint, one more constraint that I need to capture this problem, to capture this feedback vertex set? So it should be the constraint for every cycle in this collection. So what do we want here?
For every cycle, the sum of all the xv's in that cycle is greater than or equal to 1.
Yeah, exactly. We kind of want to hit every cycle. So every node in the cycle, then sum of x in the cycle must be at least 1. We need to choose at least one node in the cycle. And we want to hit every cycle like this. So that's IP. Make sense? And once you get this IP formulation, you just get LP. So I just get this thing. And again, I can ignore that XV is at most 1. Okay. So you relax this IP to LP, and then we just derive dual. Just do it mechanically, and you get this thing. And now let's try to interpret it a bit. So for this problem, it's gonna be similar actually. It looks like cycle packing. So you have a variable y, c for every cycle c, right? And you want to choose as many cycles, put value into every cycle as much as possible. But you have a constraint here for every vertex. For every vertex V, okay, there can be so many cycles go through V. So many cycles go through V. But the total value of Y of this cycle, when you sum up this cycle together, this value of cycle need to be at most the weight of W. So that's the problem, cycle packing. Okay, now let me tell you the algorithm. The algorithm gonna look like this. You start with Y, which is dual, fractional dual problem, dual fractional solution, and S, which is your primal solution, integer solution. Okay. And it kind of have similar template. So suppose that, okay, I should say G minus S, sorry. Oh yeah, actually, maybe, yeah. As long as the current graph is not a forest yet, then you need to do something. There is some cycle. So what you do, you just first, you simplify the graph. The graph can shrink a bit, but it never destroys any cycle. So it's totally safe to simplify the graph. And then once the graph is simplified, you know that there must exist a short cycle because the graph is not empty. So just choose a cycle C that is short. And then what I do, I increase y, c, for this short cycle c. Just increase this variable yc until some constant is tight. Right. You have a graph, you have some cycle c. Just increase yc. Sum of the node must be tight now. You cannot increase it indefinitely. So let's say some node is tight. It's tight at node v. Okay. When the node v is tight, just add it into your solution. And then remove v from the graph. Because you kind of you put it like you want to delete this guy. Okay. So now, so that's the algorithm. We keep doing this until the graph is a forest. So, question about the algorithms. So let me ask you first. Let me ask you about how to implement this. First, how do you find a cycle? Actually, I said that okay, there must be a short cycle. How do you find it?
BFS, like we said before.
Yeah, just from the proof. It's follow from the proof. Just do BFS. And you can find this in maybe even linear time. Yeah. Okay, so that's linear time or poly time. How about this one? When I said that I increase YC until some constant is tight, it's not like we can just do it continuously, right? You need to do it somehow in a computer in a discrete way. So how do you do this thing? Yeah.
Maybe like a priority queue, because you're going to saturate the smallest weight vertex that is in the cycle first.
So yeah, well, something like that. I mean, first of all, you know that like at least even this sum, right? You cannot list out a cycle that contain V because there can be exponentially many cycles containing V. So the sum here cannot sum them up explicitly. But what you can do, right? You can just maintain this number on every node. So that let's say that I define this thing to be a packing value on each node V. Okay. So we can maintain pack V for all V, right? And then when you have when you are given a cycle, when you choose this cycle, then you know that you have pack. Suppose that you maintain pack V for every V, right? And then if pack V of this guy is 10 and WV, which is like a capacity, is like 15, then you know that you can increase by at most 5. Like you can increase the value of YC by just at most 5. So you just kind of, every node here, you have a slack, right? So compute, you just compute min of every node in the cycle, WV minus pack V. just compute like the slack that to what extent you can increase the value of YC so that it respect the capacity, respect the constraint on every node, and just take the minimum one among all the cycle, every guy in the cycle, and increase it by that much. Then you will make some constraint tight. And once you increase the YC by that much, then you can update the pack value on every node in C. Okay. So you see, this is really polynomial time implementable, and it's like simple thing. Every step is actually simple to implement. And it gives you a feedback vertex set. Just remain to analyze it now. How good is this? Okay. So, before I finish, before we go to analysis, more question? Okay, so again, the claim is that actually our primal weight, like our primal solution can be, the weight of our primal solution can be bounded by some, like by the optimal dual cost within log n factor. And it will follow by the same reasoning that our solution is log n approximate solution. And just because like you get the same kind of sandwich, right? Our integral solution has weight at least of the IP, which is at least of the LP, which is the same as dual of dual, and you get that, you get this thing. So these two ends are within for log n factor. So between the weight of our solution and the optimal value, must be within log n factor too. So now let's try to prove to prove the claim. Okay. So again, we have that every node in our solution is tight. The sum, like this thing, is tight. Okay. Instead of this, you have equality, which means that the total weight of your set, which is the sum of everything in the set, this is exactly the sum of every cycle containing V by C. Okay, and this is now, let me swap the sum order again, summing over all cycle. This is overall V in S and V in the cycle by C. And this is just the same as, because I just sum over the same thing, sum over YC, the same YC this many times. Okay. So now I claim that like we need to, at the end we want to say that this is at most 4 log n sum of YC. So maybe it's not super clear yet why this is true, but if this is the case, then you see that we should be done, because again, sum of YC must be at most op of D, right? So why this is true again? Anyone tell me? Why sum of the YC is at most of D?
There's a dual objective.
Yeah. Sum of YC is a dual objective. And importantly, our Y respect dual constraint. Without this, we cannot say the, okay, this is at most. So Y is feasible dual solution. It respects the dual constraint. That's why you get this upper bound. So now, why this is the case? Okay. So my so beside this step, you're with me, right? That we are done. Okay, so now I claim that you will see that this is at most this, and the reason is here. It's enough for me to prove that for any y that is at least 0, then the intersection between S and C is at most 4 log n. Because if YC is 0, then it doesn't contribute to the sum anyway. Only need to bound this for YC that is positive. Okay. But for YC that is positive, it means that it's a C, the cycle that we choose, and increase the value of YC. We need to say that for any cycle that we choose, the size of that cycle intersect with the solution that we return, that is bounded by log n. So let's see why this is the case, right? So let's consider the moment that I choose a cycle C. The moment that I choose cycle C. So at that moment, the cycle is just disjoint from the solution because we have removed everything in the solution from the graph already, and we'll look at the remaining graph and take the cycle in the remaining graph. So at that point, C intersect S is empty. Okay, but you know that this cycle is short. So after we have chosen this cycle C, and we might delete we will delete one node in the cycle, right? But after that step, you might still choose some more node into your solution, but it can be only the node in this cycle. But so the number of node that you choose to delete is just from these nodes, which is short, which is not too many anyway. So like the cycle is of size 4 log n at that time. So the number of nodes that you want to delete more from this cycle can be at most 4 log n. Okay. So that's how we are done. Good. So you see, like the graph keeps shrinking. Like it's quite important to note that when we after each iteration, we simplify the graph, right? And when we simplify the graph keeps shrinking. Only we never introduce new nodes. So so if at the point of time that we choose the cycle C, there are these log n many nodes. There is no new node after that. So you can only choose the node from this 4 log n guys into your solution. All right. Okay, so that's how we get log-n approximate solution. And so let's try now to abstract out what we have done, right? Okay. So the template is going to be like this. We just start with LP relaxation. Like we have problem, get the LP relaxation, like get the IP formulation and relax it to get LP. And then you come up with the dual. And then the algorithm, what you will do is there are two things that is important. We maintain feasible dual solution at all time. Like in our previous example, we maintain y, but y is always feasible. When you increase y, you stop at the moment that it could violate some constraint, you stop. So you maintain feasible dual solution. And you allow yourself to update some primal variable, only the one that correspond to tight constraint, tight dual constraint. So this is like two important thing. Why do we want to update only the one that correspond to tight constraint? Because this is how this allows us to bound the primal cost in terms of dual variables. So let me give example, right? Because this is tight, we have equality here. We can bound the primal cost in terms of dual at the end, because this is the equality instead of this equality in the wrong direction. The same for like the log-n approximate for feedback vertex set. So that's how we the two things that is important: feasible dual solution and update primal solution only for the tight constraint that correspond to tight dual constraint. So it turns out that this way is a very powerful way to design algorithm. And the punchline is that it captures everything that you know. Like Dijkstra actually can be derived from this framework. For Ford Focus and Kruskal, I think you have seen it maybe in previous class, which is the algorithm for computing minimum spanning tree, and some other things, and many other approximation algorithms. It can be derived from this framework. You start with primal and dual and try to update the solution like this. And once you get an algorithm, it might not be clear at all that it's come from this, come from like when you start with LP, because you see that every step of the algorithm is just so clear, like nothing is LP based, but you can derive it from this guy. Okay. Now I want to tell you about one concept, which is integrality gap. Okay. It's an important concept when you work with LP. Okay. So it's a concept that can help you to answer how good is this LP that you're working with when you try to come up with approximation algorithm. So before I tell you why, let me tell you what it is. Suppose that the problem that you look at is a minimization problem, call it X. And then Pint be the integer program for X, and P be the LP relaxation. Then the integrality gap is just asking what's the difference between the two, like between the integral solution and fractional solution. So So maybe I should say that should be maximize overall instant I in overall instance I for x for the problem x and the opt of p int when you have instant I and off of p with instant I. So it's like you ask how much the integral version and the fractional version can differ. Okay. And there is some problem that is good for this. For some, like if the gap is big, then it's bad. The gap is 1, then it's good. Okay. Actually, you have seen some problem where the gap here is 1 already. Can you tell me what's that problem? We have seen this problem in class before.
Maxwell.
Yeah, max flow is a 1. So, like, even if you reduce, like, even if you allow fractional value, it doesn't help you to get better solution. There's always exists of integral solution that is as good as fractional one. So there's no gap for max flow. But in general, there can be a gap. And the observation is that whenever you design an algorithm based on some LP, P, then your approximation ratio will be at least as bad as integrality gap. And the reason is just this. So when you design approximation algorithm, right, you want to come up with some integral solution. And when you base yourself on LP, you usually just compare your value of your solution with the optimal value of the LP. So you want to bound this thing, gap between your solution and the best fractional one. But integrality gap says that, okay, even the best integral one and fractional one, this gap is big. So there's no way to get better than the integrality gap. Okay. So let's see some example when the gap is not 1, right? So the example is maybe vertex cover. Yeah. For vertex cover, you have this IP that says that, okay, you can choose each node into your set such that for every edge, you must choose at least one of its endpoint and you minimize the cost. Okay. And if you consider, let's say the complete graph, right? For complete graph, you know that no matter what, the optimal solution must have size n-1. Because if you miss 2 nodes, then there is an edge between them. So you need to delete, you need to choose this optimal size is n-1. But for fractional one, you could just set every node to be 1/2, and it would cover every edge. So which means that, okay, sorry, the optimal fractional solution is at most n/2. So it means that the gap here is basically as close to n as it can. And what we did is we designed two approximation algorithm, so it matched the gap. So it matched to the best possible that this LP can give you, and actually it matched it not just even match the limitation of this LP, it even match the hardness. So, okay. So how about feedback vertex set? So I claim that it turns out that the gap is locked in. And this is not clear. I will just mention why. So it turns out that there is something called Ramanujan graph. You can look up what it is, but it is some kind of like, it's the best expander. Like optimal expander in some sense. And I will not explain it, but this graph has the following cool properties. It's a graph such that every short cycle, there is no short cycle. Every cycle has length at least log in. Okay. And if this is the case, then it means what? It means that if you just set xv to be 1 over L for all nodes, that gives you the feasible solution for this fractional problem. So it means that the optimal fractional solution for this LP is actually just n over log n. But at the same time, this Ramanujan graph is such that if you look at any set such that its size is quite big, okay, any set that is of size like 3n over 4, it will contain cycle. No matter what set it is, like if you take some set here and here such that the total size is 3n over 4, there must be some edge crossing this and crossing this and this cycle. And it means what? It means that your solution must have size at least 3n over 4, because otherwise, your solution must have size n over 4, more than that, yeah. Otherwise, the remaining part is greater than this, and it contains a cycle. So it means that the gap here is like is log n. The fractional one is small, n over log n. The integral one must be of order n. So the gap is log n. And it means what? It means that for today's algorithm that gives you log n approximation, this LP really, like, we reach its limitation. We reach the limitation of this LP. We cannot go beyond log n. This is optimal with respect to this LP. But I said before that there actually exists the two approximation algorithm. So it means what? It means that, and actually that algorithm is based on some LP as well. So it means that this guy must be based on different LP. So the point is, you start with some problem. There's some natural way to come up with the LP that captures the problem. This LP might be good to some extent. It might not be the best. There is some more nicer LP that maybe gives you better. So you see, like, to come up with LP or IP relaxation, there is some limitation on the different one that you come up with. Okay. So that's the point. So now, just to wrap up, so now you have seen 3 ways to get the approximation algorithm. One is kind of ad hoc, one is LP routing, another is primal-dual. And as you see, as you see, like we kind of use LP to come up with algorithm, but we never solve LP. So yeah, you see that LP is not just a powerful black box. It's a tool for you for design algorithm. And in next class, we will go to online algorithm. And it's going to be similar to approximation algorithm. But now it's cool in the sense that it helps you to make decision for future. That is a good one without knowing future. So that's the topic of next week. Yeah, see you then. Yeah.